The James Webb Space Telescope has just dropped a bombshell in the world of physics, shattering what scientists thought they knew about the universe with a single stunning image. It's rewriting the rules and ending a fiery debate that's raged among scientists. Webb's latest caption is not only visually fascinating, it's an eye-opener that's enhancing our understanding of the cosmos. Get ready to rethink everything. The crisis in cosmology refers to a significant and persistent problem in astrophysics. The age and expansion rate of the universe as estimated by different methods do not agree. This discrepancy has puzzled scientists and sparked a series of debates and research efforts to understand the underlying cause. Cosmology, the study of the universe's origin, structure, evolution, and eventual fate, has made substantial progress over the past century. The Big Bang Theory, which suggests that the universe has been expanding from a hot initial state for about 13.8 billion years, is the prevailing cosmological model. This expansion is characterized by the Hubble constant, a value that represents the rate at which the universe is expanding. There are several ways to measure the Hubble constant, broadly falling into two categories: local measurements and early universe measurements. Local measurements involve looking at astronomical objects within the universe, such as Cepheid variable stars and type Ia supernovae. These are known as standard candles because their intrinsic brightness is well understood, allowing astronomers to calculate their distances from us. By measuring the speed at which these objects are moving away from us, thanks to the expansion of the universe, scientists can estimate the Hubble constant. On the other hand, early universe measurements are derived from observations of the cosmic microwave background radiation, the afterglow of the Big Bang. The CMB is a snapshot of the universe at a much younger age, only 380,000 years after the Big Bang. By studying the slight fluctuations in temperature and polarization of the CMB, scientists can infer not only the age of the universe but also its rate of expansion. The crisis emerged when astronomers realized that these two methods were giving significantly different values for the Hubble constant. Local measurements suggest the universe is expanding faster than what is predicted by observations of the CMB. This discrepancy suggests that there may be new physics at play that we do not yet understand, or there could be systematic errors in one or both sets of measurements. The advent of the James Webb Space Telescope brought fresh insights into this problem with its unprecedented resolution and sensitivity. The JWST has been able to look further back in time and at fainter objects than ever before. It was anticipated that the data from JWST would help refine the measurements of the Hubble constant. However, early observations have seemed to complicate the picture even more, providing new data that may not fit neatly within our existing models. The implications of this crisis are far-reaching. If the discrepancy is due to new physics, it could require a revision of the standard model of cosmology. For instance, there could be previously unknown particles or forces affecting the universe's expansion. Alternatively, it might hint at the need for a new understanding of dark energy, the mysterious force that is thought to be accelerating the expansion of the universe over time. Theories in cosmology have evolved as new observations have challenged existing models. For instance, the discovery of the CMB in 1965 provided strong evidence for the Big Bang theory and against the steady-state theory. Similarly, the discovery of the accelerating expansion of the universe in the late 1990s led to the introduction of dark energy, a concept that was not part of the original Big Bang theory. Each time new data has been introduced, cosmologists have had to examine the robustness of their theories and, in many cases, develop new theories or modify existing ones to account for the observations. The current crisis may similarly lead to significant advancements in our understanding of the universe. While the crisis in cosmology presents a formidable challenge, it is also an exciting opportunity. It drives technological advancement as scientists require more precise instruments to make better observations. It fosters collaboration across international and interdisciplinary boundaries, as understanding the universe is a question that intrigues nations and fields alike. Most importantly, it exemplifies the dynamic nature of science, where knowledge is never absolute but constantly evolving as we expand our horizons and deepen our understanding of the cosmos. Cosmology, the study of the universe's origin and evolution, has faced a new challenge beyond the well-known Hubble tension, the SA tension. This tension centers on the distribution and density of matter in the universe, a fundamental aspect that helps us understand the cosmic structure and its history. The concept of lumpiness refers to how matter is not evenly spread out across the cosmos. Some areas are dense with galaxies, while others are vast voids of almost nothingness. Scientists use different methods to measure this lumpiness, and that's where things get tricky. One method is through low redshift observations, particularly with weak gravitational lensing. Gravitational lensing occurs when the gravity of a massive object, like a galaxy cluster, warps the space around it and bends the path of light passing by. This effect allows astronomers to map the distribution of dark matter, the unseen stuff that doesn't emit light but has a gravitational pull. Weak gravitational lensing involves looking at the subtle distortions in the images of distant galaxies caused by the less dense and therefore weaker gravitational fields of large-scale cosmic structures. On the flip side, scientists examine the cosmic microwave background, CMB, which is the afterglow from the Big Bang. This light has traveled for about 13.8 billion years, carrying with it information from the early universe. By studying the CMB, scientists can infer the early lumpiness of the universe, which should align with the large-scale structure we see today. Here's where the SA tension comes in: these two methods don't agree. The clumpiness measured from the CMB suggests a smoother distribution of matter compared to what is observed directly in the nearby universe using gravitational lensing. This discrepancy points to a possible gap in our understanding of the universe's evolution from its smooth beginnings to its current clumpy state. The resolution to this tension could lead to revolutionary changes in cosmology. If the measurements are accurate, it may hint at new physics, requiring an update to the standard model of cosmology, the framework that describes the dynamics and content of the universe over time. Theories of the universe have evolved dramatically. For instance, the Big Bang theory, which posits that the universe began as a hot, dense point and has been expanding ever since, was once contentious. Evidence like the CMB and the observation of the expanding universe has since turned it into the leading theory of cosmic origin. Another area where our understanding has progressed is dark energy. In the late 1990s, observations of distant supernovae revealed that the universe's expansion is accelerating, not slowing down as previously thought. This led to the concept of dark energy, a mysterious force driving this acceleration. Its nature remains one of the biggest questions in cosmology. The James Webb Space Telescope, JWST, is poised to push the boundaries of our cosmic knowledge further with its unprecedented resolution and sensitivity. The JWST will peer into the earliest epochs of the universe, examining the first galaxies and stars. It will also, refining our measurements of cosmic expansion and the distribution of matter is crucial. Addressing the SA tension will require meticulous observation and possibly new theoretical insights. Whether the resolution lies in understanding dark energy better, accounting for the behavior of dark matter, or finding entirely new physics, the implications will be profound. Cosmology's crises, such as the Hubble and SA tensions, are not stumbling blocks but stepping stones. They drive the field forward, leading to better instruments, more precise observations, and deeper theoretical insights. Each challenge brings us closer to answering the most fundamental questions about our universe's past, present, and future. When we confront the mysteries of the cosmos, it's like trying to solve the world's biggest jigsaw puzzle without having the picture on the box. Scientists, the dedicated puzzle solvers, are tirelessly piecing together the universe's secrets. They recently upped the game with a project known as Flamingo, which is a nod to the extensive scientific research it stands for. The Flamingo project isn't a usual science experiment, it's a heavyweight of computational might, utilizing one of the planet's most powerful supercomputers at Durham University in the UK. Its scale is so vast that it gobbles up over 50 million hours of computer time and sprawls across 30,000 processors. This is no small feat. It's the scientific equivalent of running a marathon on every continent back to back. Earlier attempts to simulate the cosmos focused primarily on dark matter, the enigmatic stuff that doesn't emit, absorb, or reflect light but has a gravitational pull. Flamingo, on the other hand, was ambitious. It wasn't just about dark matter anymore. The simulation included everything from the behavior of galaxies to the gas inside them, the stars, and even the supermassive black holes at their centers. It's as if we went from having an incomplete map of the world with only land masses to one that shows mountains, rivers, and every landmark in exquisite detail. But why go to all this trouble? The goal was clear: to understand the SA tension better. This tension, a discrepancy in the measurements of the universe's structure, suggests there's something fundamental about the universe that scientists are not getting right. If the measurements were songs, it would be as if one was jazz and the other classical, both music but distinctly different. Flamingo was supposed to help iron out these discrepancies, to let us know whether we were looking at the universe through the wrong lens. But despite its sophistication and detail, the SA tension remained. It was like using the most advanced metal detectors to find buried treasure, but still, the treasure remained elusive. The persistence of this tension is a sobering reminder that there's still much to learn. The universe, it seems, isn't ready to give up its secrets so easily. Every new piece of data, every simulation like Flamingo, is a step forward but also a new riddle to solve. It's a complex back and forth where each answer leads to more questions. Since the early 20th century, when Edwin Hubble discovered that the universe was expanding, our understanding has grown in leaps and bounds. Scientists have learned about the Big Bang, dark matter, and dark energy. They've peered back in time with the cosmic microwave background and mapped the positions and velocity of galaxies with increasing precision. Each of these milestones has been like finding a corner piece of the cosmological puzzle. Yet, the universe doesn't yield its secrets easily. With every new discovery, we adjust our theories, refine our models, and sharpen our questions. The Big Bang Theory, once a radical idea, is now the cornerstone of textbook science. The concept of dark matter has evolved from a wild guess to a key component of our cosmic model. Dark energy, a repulsive force accelerating the universe's expansion, was unknown until the late 20th century and now is central to our understanding of the cosmos. In the face of the SA tension, our quest continues. The James Webb Space Telescope, a successor to Hubble, offers even deeper insights into the universe's infancy, providing data that will test and challenge our models like never before. In the vast expanse of the cosmos, there's a dance of particles and forces that has been going on since the dawn of time. But it's not just a waltz of stars and planets, it also offers a deep mystery that has had astronomers playing the sleuth for centuries. Let's talk about how they've been trying to crack the case of the universe's expansion and why, despite their best efforts, some pieces of the puzzle just won't fit. Long ago, people thought everything in the sky revolved around the Earth. That idea was shelved when Copernicus and Galileo came along, arguing that Earth and the other planets orbited the Sun. It was a mind-blowing shift. Fast forward to the 20th century, and we've got Einstein shaking things up with his theory of general relativity, suggesting that space and time are part of a four-dimensional structure he called spacetime. Einstein's ideas set the stage for a universe that was far from static, it was expanding. In the 1920s, Edwin Hubble observed that other galaxies were moving away from us. Hinting that the universe was getting bigger all the time, this led to the revolutionary idea that the universe started as a tiny speck that suddenly inflated and has been expanding ever since. For a while, everyone thought gravity would slow this expansion down, but in the 1990s, astronomers found that not only is the universe expanding, but it's also doing so at an accelerating pace. This was as shocking as discovering that instead of slowing down after throwing a ball up in the air, it speeds up into the sky. To explain this, scientists proposed the existence of dark energy, a mysterious force that's pushing the universe apart. Now let's fast forward to our current puzzle, the SA tension. This tension is about the clumpiness of the universe, how matter is distributed across the vast cosmic web. When we look at the universe on a large scale, it looks like a foam with galaxies and clusters of galaxies strung along filaments surrounding giant voids of seemingly empty space. To measure how clumpy this cosmic web is, scientists use different yardsticks. One method is to study the cosmic microwave background, CMB, the afterglow of the Big Bang, acting like a snapshot of the infant universe. The CMB has been incredibly useful, giving us a map of the early universe and telling us how matter began to clump together. The other method is to look at the universe more locally in the present day by observing how galaxies are distributed and how light bends around them, a phenomenon called gravitational lensing. The two methods give us different pictures of the universe's lumpiness. The Flamingo project played a pivotal role in this arena. This isn't just a supercomputer simulation, it's like the most intense virtual reality model of the universe ever made. It uses data from both the CMB and observations of galaxies to create a universe in bits and bytes. The aim is to see if, given the laws of physics as we understand them, the early universe could evolve into the one we see today. Flamingo tried to model the universe with both dark and ordinary matter. This was a big deal because previous simulations mostly left out the latter. It's like trying to understand how a car works by only looking at the frame without considering the engine, seats, or wheels. The results were impressive. Flamingo could make galaxies that look like the Milky Way. But when it came to the clumsiness measured by the CMB and the local universe, it still couldn't resolve the tension. The universe's expansion rate and the way matter clumps together just didn't syn up. This leaves astronomers searching for answers. Some say we might need new physics, new laws to explain what we see. Others think our measurements or understanding of dark energy might be off. It's a classic enigma, with the universe playing the role of the central puzzle. As we stand now, despite our powerful telescopes and brainy simulations, we've got a cosmic cliffhanger on our hands. And that's the beauty of science, it never ceases. Each question unlocks a journey of discovery. Every observation and every simulation is another step toward understanding the grand story of the universe. In this cosmic tango, it's clear the music isn't stopping anytime soon. The SA tension is more than just a scientific conundrum, it's a reminder that there's so much more to learn. And as we keep studying the stars, there's an anticipation of what secrets the universe will reveal next. The universe has always been a vast frontier, rife with enigmas, and our quest to understand it has been relentless. The theories scientists have built to explain the cosmos have been evolving, shaped by a series of revelations and sometimes revolutions in thought. Let's walk through this journey of cosmic discovery and see how our perspectives have changed, especially in light of the recent challenges posed by new observations. Way back, the ancient Greeks set the stage with a geocentric model where Earth sat at the center of a universe that wasn't too large. It was a straightforward idea but not accurate. Later, in the 16th century, Copernicus made a breakthrough with a heliocentric model, placing the Sun at the center of our solar system, which better explained the motions of the planets we see. Isaac Newton entered the arena in the 17th century, giving us the laws of motion and universal gravitation, concepts that stood unchallenged for centuries. These laws worked wonderfully for predicting the movement of celestial bodies within our solar system and became the bedrock of classical physics. The 20th century began on an exciting note as Einstein introduced his theory of general relativity, profoundly changing our understanding of gravity. This theory opened up a whole new way of looking at the universe as a fabric of space and time capable of warping and bending. It paved the way for understanding cosmology as we know it today. In the 1920s, Edwin Hubble discovered that galaxies were moving away from us, leading to the revolutionary idea that the universe was expanding. This was a monumental shift from the static universe concept and led to the Big Bang theory, which posits that the universe started from a hot dense state and has been expanding ever since. The precision in our cosmic measurements took a leap forward with tools like the Hubble Space Telescope, which allowed us to measure the rate of this expansion. However, this is where things started to get puzzling. The expansion rate, called the Hubble constant, appeared different depending on whether we measured it using the light from nearby galaxies or from the cosmic microwave background CMB, the faint afterglow of the Big Bang. The discrepancy between these measurements became known as the Hubble tension, and just when we thought we had enough on our plate, another discrepancy arose, the SA tension. This refers to the difference in measurements of how much matter there is in the universe and how it's distributed. The universe appears less clumpy than our models predict. The James Webb Space Telescope with its advanced capabilities has provided us with sharper images and data that add layers to the existing tensions. It shows galaxies that seem to be more spread out than what our current theories anticipated. Despite the best efforts including elaborate simulations like the Flamingo project, which was designed to incorporate the effects of ordinary and dark matter, we still see a mismatch. Flamingo aimed to reconcile our models with observations, but the universe proved more rebellious than expected. So where do we stand now? Our models of the universe are being challenged. We're in the midst of a potential paradigm shift where our theoretical foundations may need to be revisited and revised. These are not setbacks but signposts that point us toward a deeper understanding. Each new observation that doesn't fit our models is a clue that could lead us to new physics, to new explanations of the fundamental workings of the cosmos. The beauty of science lies in its self-correcting nature. Each discovery builds upon the last, each anomaly or tension pushes us to refine our theories and our view of the universe. The dance of the cosmos is intricate, with each step meticulously choreographed by the laws of physics. Yet, as we peer into the vastness of space with ever more powerful instruments, we find that some steps are out of sync, prompting us to learn new moves. Scientific exploration of the cosmos is far from over, with advanced telescopes, increasingly sophisticated simulations, and a community of scientists tirelessly seeking answers. We continue our quest. The universe is not just a frontier, we're in the midst of a potential paradigm shift where our theoretical foundations may need to be revisited and revised. These are not setbacks but signposts that point us toward a deeper understanding. Each new observation that doesn't fit our models is a clue that could lead us to new physics, to new explanations of the fundamental workings of the cosmos. The beauty of science lies in its self-correcting nature. Each discovery builds upon the last, each anomaly or tension pushes us to refine our theories and our view of the universe. The dance of the cosmos is intricate, with each step meticulously choreographed by the laws of physics. Yet, as we peer into the vastness of space with ever more powerful instruments, we find that some steps are out of sync, prompting us to learn new moves. Scientific exploration of the cosmos is far from over, with advanced telescopes, increasingly sophisticated simulations, and a community of scientists tirelessly seeking answers. We continue our quest. The universe is not just a frontier, it's the ultimate puzzle, and piecing it together is perhaps the most grand and exhilarating challenge humanity has ever faced. Stay curious, stay engaged, and watch as we continue to explore, discover, and understand the marvels of the cosmos. The journey is bound to be filled with more surprises, and each one will bring us closer to answering the age-old question, what is the universe, and what is our place within it? What do you think lies ahead in this cosmic journey? Let us know in the comments below. See you in the next one.